All right, so in this particular incline problem with the pulley, or an Atwood machine, we have a system here where there's an M1 of 10 kilogram that is resting on a frictionless surface, and then we have a hanging block of 9 kilograms to the right of the system. All right, and it says the angle alpha is given as 55 degrees here, and part A1 is to calculate the magnitude of the net force on just M1, so this block that is resting on the incline surface, and then B as is to find the magnitude of the acceleration in the system. Because they are hooked up together to a one string, both accelerates at the same rate. And then C, determine the magnitude of the tension in the cable. So here's the cable that connects M1 and M2. So this is pretty straightforward since there's only one string and two blocks. All right, let's go and crack it out. As usual, draw out your forces. This way you don't miss anything. Here, this black vector is f of g2. F of g2 is going to be pointing down straight the page here, which is just mg, m being 9, g being 9.8. So the magnitude of f of g2 is 88.2. So you notice here the value of f of g2 is a positive quantity, 88.2, because I will take the line of motion to be positive. But for now, it's a good idea to find out your forces before you determine the line of motion. So you don't know whether the system is moving left or right yet, but you can run a quick test. Okay. Here, this is f of g1, m1, even though it's on the incline surface, the weight of it is directed down the page or directed down the screen. This is f of g1. Because f of g1 now is in between the x and y axis. A quick reminder, for inclined surfaces, we take the surface, the incline, as x-axis, or in this system, we take the line of motion, which is up the incline, and then down to the right as our line of motion, which is the x-axis, which is wrapped around. And then here, this component is f of gy, because y is perpendicular to the x-axis. Okay. So this is f of g1y, and then f of g1x is pointing down the slope. A quick reminder, f of gx is always directed down the slope regardless of how the ramp is given to you. All right. Other than that, this makes a right triangle, and then the angle given here is 55 degrees. Alpha, the angle of the ramp is 55 degrees, so therefore the angle between f of g and f of gy is all the same angle, so that's also 55 degrees where my cursor is kind of tracing back and forth. Okay, so whatever the angle of the ramp is, the angle between f of g and f of gy will be the same based on geometry proof. All right, let's go ahead and crack out part A. To do part A, I think it's the quickest to go ahead and find f of g1x. In this case, we know the motion is moving along the surface of the incline, aka our x-axis, which happens to wrap around the pulley. So we take the line of motion to be our x-axis. So our x-axis is kind of actually wrapped around this pulley system. Okay. So therefore, let's go ahead and find f of g1x. To find f of g1x, we need to use sine of theta. Sine of 55 degrees by definition is opposite, which is in this case fg1x over hypotenuse. Hypotenuse in this case is fg1 because that is the length facing the right angle. So my cursor is tracing back and forth between the y and the x-axis. That makes 90 degrees. The leg that is the opposite from that is your hypotenuse. So sine by definition is opposite over hypotenuse. So is the opposite in this case would be fg1x. And then our hypotenuse f of g1. In order to solve for fg1x, we multiply both sides by f of g1, which leaves us with fg1 sine theta is equal to fg1 in the x direction, or along the surface of the ramp. But we know that by definition, f of g can be broken down to mass times gravity. Here, because f of g1, we use mass 1. G does not have a subscript because it's just a universal constant. And then sine of theta. So therefore, we just plug in values. M1 is given as 10 kilograms. Right here, this is the mass M1 that is resting on the surface. That is 10 kilograms. G is 9.8, and then sine of 55 degrees. And then here, we just plug the calculator work, and our magnitude for f of g1x is 80.28 newtons. All right, now the question is, what do you do with this value once you get this, right? So I tell my kids to use common sense. Here, the line of motion is up the ramp and then down to the right. Well, if you use common sense, f of g2 is 88.2. The only thing acting against this motion in the x direction that's wrapped around the pulley is fg1x. Because if you stretch the system up to a horizontal surface, f of g1x points to the left, fg2 points to the right. So therefore, f of g2, which is 88.2, f of gx we just calculated is 80.28, which is less than 88.2. So therefore, the system is going to favor the rightward motion. So watch where my cursor is. 88.2 is larger than fg1x. Therefore, the system is going to move to the right, aka m1 is going to move up the ramp, and then m2 is going to fall down. Okay. So therefore, the easiest way to find part A, I like doing percentages. Hopefully, you've seen my other videos. So we can say the net force acting on m1 is the percentages of the net force. So here, the numerator is 10 kilogram because I'm looking at m1. The total mass of the system is 19. So there's a certain percentage here. Okay. So I like percentages. So it'd be 10 out of 19. That gives you a percentage. A percentage of what? A percentage of the net force. So this particular quantity in parentheses here is your net force. I know this is the net force of the system because, well, the weight of m2, which is 80.2, is going to cause the system to accelerate to the right. But at the same time, though, being on the incline, m1 has an f of gx points down the ramp, which in this case acts against the object's motion. Okay. Or the system's motion, however you want to look at it. So the m1 can only slow the motion down. So you need to subtract. That's just using common sense. Therefore, we take the weight of m2 minus f of g1x, and the difference there is going to be 7.92, and then 10 divided by 19 is 0.526. So about 52.6% of the net force is going to be allocated to m1, which makes sense because this is 10 kilogram, this is 9. So 10 is more than 9. So, you get more percentages. Okay. So therefore, the net force on this two, the net force on m1, if you multiply these two values together, would be about 4.2 newtons. Okay. So that's the answer for part A. Now, I like percentages. So if you like it, use it. If not, just stick to Newton's second law. And here, this is the other way to do it. The net force on m1 is simply the mass of itself times the acceleration of the system. Well, here I know the mass is 10 because it asks for m1, right? But I don't know what the acceleration of the system is. But to find the acceleration of the system, it's pretty easy to do. All you have to do is look at what the force is causing the system to accelerate. In this case, it'd be f of g2. And is there an opposing force against the motion? Well, in this case, there is. It's f of g1x that's pointing down the ramp, which acts against the object's motion. So therefore, in order to solve for A, I would just divide both sides by m total. So we have A is equal to net force of the system divided m total. But net force of the system is easy. It would be the weight of m2, which is the hanging block, subtracted from fg1x, which is pointing down the ramp. And pointing down the ramp would be, in this case, against the object's motion again, because the m1 wants to move up the ramp based on our reasoning here. Okay. So therefore, f of g2 would be 88.2. F of g1x would be 80.2x, which is calculated right here for you. And then the total mass of the system would be 19 kilograms because 10 plus 9 is 19. So if you take the difference on top and divide it by 19, you should get a value of 0.42 meters per second squared. So that's the magnitude of our acceleration. Well, all you have to do is plug it back in. We earlier stated that the net force for m1 is simply its mass times the acceleration. Well, we just find the acceleration as 0.42. So I'm just going to carry this work down. Mass is 10 kilograms. I substitute in for 0.42 meters per second squared because that's what I just calculated. Therefore, 10 times 0.42 is 4.2, which is the same answer as we got on the left bottom of the screen here. Okay, so if you like percentages, use it. If you don't, just go ahead and apply Newton's second law. It's safe. Hopefully, you can just crank out the calculator work. So the answer is exactly the same. All right, so let's do part B. Part B asks us to calculate the magnitude of the acceleration system. Actually, as a matter of fact, we just found it already. By using the second strategy in order to find net force of m1, we actually had to find the acceleration of the system. So therefore, I'm just going to box this and highlight it. The answer for part B is 0.42 meters per second squared. So the difference between percentages is that I don't have to go through acceleration because I can just look at the system as a whole. Well, if you'd like to use Newton's second law, which is sigma FMA, you have to know what A is. So in this case, we just happen to find A, and that's the answer to part B, which is okay. All right, let's do part C. Part C asks you to determine the magnitude of the tension in the cable. So I'm seeing there's only one string that's connecting M2 that's wrapped around this pulley, and it connects to M1 that connects around to M2. When it comes down to T, pick the box that's less work. I think in this case, I want to use M2 because it is less work. Okay, if you pick M1, you have to go through like all the cosine sine stuff, right? M2 is just hanging. So therefore, to find the tension, I will focus my attention on M2 because it is the easier one to do, not the only one. It's just easier. So there's T. I drew T a little smaller because in this case, we deducted that f of g2 because it is bigger. It's going to cause the system to move rightward because it's moving rightward. The tension in this case would have to be a little smaller. So not drawing a scale, but I do know that T here has to be a little smaller than f of g2. So if I set up Newton's second law of motion for M2, I have sigma F equals ma. Well, sigma F M2 because I'm just looking at M2. The right side is M2. And then we already know that using common sense, f of g2 is bigger than t. So I'm going to say the line of motion is favoring the right. So therefore, I'm going to take f of g2, which is causing the system to accelerate to the right, minus what's opposing it, which is t. Again, this tension here is attached to this cable, and this cable has a weight to the left side, which is, I like to call it dead weight. It acts against you, so it can only slow the system down. In this case, slowing something down would suggest that you're subtracting. So therefore, we do f of g2 minus t, which is equals to m2a. To solve for t, I say for t by moving this negative t to the right side of the equal sign, which makes it positive, and then move the m2ax to the left side, which changes sign. This is positive, so moving it would cause it to be negative. So we know f of g2 already, which is 88.2, and then mass is 9, because I'm looking at m2. Acceleration we found already, which is 0.42 right here. Okay, where my cursor is going back and forth. And then if we plug that into our calculator, we should get a value of 84.42. Okay, so the tension in this case would be the same magnitude whether you're looking at M1 or M2. So the magnitude here is going to be 84.42 newtons. All right, I hope that helps. Good luck. Stay nerdy. Don't be whack.